Welcome everyone for this afternoon session. So it's a pleasure to introduce Zev Rosengarten, who will speak about rigidity and irrational groups.
Hey, thank you. And thank you to the organizers for organizing this very nice conference and for inviting me to speak. Yeah, so the title is Rigidity in International Groups. A better title might be something like just some musings about unipotent groups and unirational groups, but we'll see. So okay, so just probably almost everybody, if not everybody here knows this, but just to refresh you, the upper triangular unipotent group is a sort of the canonical example of a unipotent group. So it's just a group of upper triangular unipotent matrices. You have one n by n, you have ones along the diagonal and whatever you want above and zeros below. And for example, the group U2, that's just the additive group GA. Okay. And an arbitrary unipotent group over a field is a closed subgroup or subgroup variety of one of these groups UN. Okay, so these groups UN admit a filtration with successive quotients isomorphic to GA. So have something like UN, I'll just call it U. U is, let's say, Vn, contains n minus 1. Is this in the bad part?
Yeah, I think you should.
Is this the good part?
That's the good
part.
So U is, let's say, Vn, and then you have this normal subgroup Vn minus 1, and so forth. V whatever, V0 is trivial. And then Vi mod Vi minus 1 is all isomorphic to the additive group. So you have a filtration like this. So these groups, these upper triangular unipotent groups are solvable, and in fact, they're even nilpotent. And in characteristic P, if you feel this characteristic P, they're P power torsion, because the group GA is P torsion. And an arbitrary unipotent group is a closed subgroup variety of one of these groups. And so it inherits these properties. They're nilpotent, in characteristic P, they're P power torsion. And a special property of the groups UN is they admit a filtration, as I said, the successive quotients isomorphic to GA. So we say that they're split unipotents. That's just what it means for a unipotent group to be split. Okay, so maybe I won't use this, but maybe I'll just say, in characteristic 0, any unipotent group is necessarily smooth and connected. But in characteristic P, you can have extra groups like, is this good?
Yeah.
Okay, you can have extra things like alpha P and Z mod P. These won't really come up in this talk, but just to let you know, these are also unipotent in characteristic P. Okay. Yeah, I guess I should know where the okay. Okay, so here's a definition. So I just mentioned split. So a smooth connected unipotent group over a field K is called K-wound, or just wound if we know what the field is, if it doesn't contain a copy of the additive group over K. So there's some equivalent conditions. It's not entirely obvious that they're equivalent, but they are. So one definition is U doesn't emit a non-zero homomorphism from the additive group. And another is that there's no non-constant map from the affine line. So of course, if there's no non-constant map from the affine line, there can't be a non-zero homomorphism from the additive group, which as a variety is just the affine line. But the converse, it turns out, is also true. Okay, and now over a perfect field, for example, a field of characteristic 0, every smooth connected unipotent K group is split. And so there are no non-zero wound unipotent groups. And then some other basic properties. It's preserved upon passage to separable extensions. So if you have a separable extension and U is K wound, it's an if and only if, but one direction is trivial. U is K wound, it's separable, and U is K wound if and only if UL is L wound. Okay. So it behaves in the opposite manner for a torus. Splitness is splitness. If this extension is purely inseparable, then splitness over K or anisotropicity over K is the same as over L. And unipotent groups have the opposite behavior. Okay, and then maybe one thing I should say here is the fact that over a perfect field, everything splits, every smooth connected unipotent group, means that if I have a unipotent group over any field K, then it splits over the perfect closure. So this is split because this is perfect. And then that means it descends to some finite extension. So UL is split for some finite, purely inseparable L over K. Okay. Okay, so here's an example of a non-trivial such group over any imperfect field. So as I said, the field has to be imperfect to have such examples. So let K be imperfect and choose a non-Pth power. The fact that K is imperfect exactly says there is such an A. And you consider this group U, which is defined by just this equation inside of GA squared. So y to the P minus AX to the P minus X is 0. So I claim that this group is wound unipotent. So what do we have to check? Well, you have to check actually that it's smooth and connected. Let me not worry about that right now, but I need to check that there's no non-constant morphism from the affine line over K. Okay, so such a morphism is the same thing as just a pair of polynomials, x of t and y of t, not both constant, which satisfy this equation, right? And so if you just stare at this equation, you see that because they're not both constant, x and y have to have the same degree. And so if you let little y and little x be the leading coefficients of these polynomials, then you just compare the leading coefficient on both sides, you get y to the p minus ax to the p is 0. And then if you just solve for a, right, you get that if x is not 0, you would solve for a, and you get a is y over x to the p, which is a Pth power. So that's a contradiction. So x has to be 0, and then you get that y also has to be 0. Okay, so you get this contradiction, and so there's no non-constant such matter. And I should say that this actually, so as you expect, this thing should become split over a purely inseparable extension. And in fact, if you extend scalars to a to the 1 or k join a to the 1 over p, you take this purely inseparable extension, then you have an isomorphism between u and GA. The way you find this is you have this y to the p minus ax to the p is x. And so basically, you think so this is y, this left side is p x to the p, and you send xy to this source. And then to go the other direction, you need to recover x and y from t. So x is t to the p. And then y, so you solve y minus a to the 1 over px is t. So y is t plus a to the 1 over px, and x is t to the p. So this is an isomorphism over this extension field. But there's no such isomorphism over K. Okay. And you can construct much more complicated examples. There are non-commutative examples. These things can get very, very complicated in general. Okay, this is just a simple example. Okay, so let me mention this theorem. This question, this theorem, and then really this question motivated a lot of the work, really all the work I'm going to talk about in this talk ultimately. So in his very nice 1984 paper on Tamagawa numbers and unipotent groups, Osterle proved the following result. So let K be a global function field. Okay, so that just means the function field of an integral curve over a finite field. So the sort of classic example would be you take the field P1 over FQ, or sorry, the curve P1 over FQ, and the function field is just the rational function field. So this would be an example. So let's say K is a global function field, and U is a wound unipotent K group of dimensions strictly less than P minus 1. Then the conclusion is that U has only finitely many rational points. Okay, now this is kind of strange. I mean, for one thing, it's a fact that if K is perfect, then every smooth connected linear algebraic K group is unirational. A group is unirational. And so in particular, if your field K is infinite, then it has a Zariski dense set of rational points. Okay. So in this case, you see that these things are not unirational. In fact, they only have finitely many rational points. Maybe actually, just to give you a flavor as to how you prove this kind of thing. I mean, I'm not going to give you the proof, but a sense as to the kind of manipulation that allows Osterle to prove this kind of result. Let me take the example from the previous slide. So y to the p, yeah, maybe I'll write it this way. So I'll change things a little bit, but y to the p is x minus tx to the p. That's with a is negative t, and you take k to be this field. It's an example in the previous slide. So this inside of GA square. This will be my group. And if p is bigger than 2, okay, so first of all, U has dimension 1. This is less than p minus 1 if p is not 2. When p is 2, this thing's actually unirational. So when p is 2, it actually has lots of rational points. But when p is not 2, Oesterle's theorem says that U should have only finitely many rational points. It should have only finitely many K points, where K is this field. And so one way to prove this is just, suppose I have a solution to this. So y to the p is x minus tx to the p. Okay, so the differential y to the p is p y to the p minus 1 dy. And characteristic p, that just vanishes. So you get 0 is dx. And similarly, dx to the p vanishes, so you get minus x to the p dt. Okay, so we get dx is x to the p dt. Now, if you look at a point, let's say a point v, a closed point v, and this way. So this is a closed point of this curve, and you ask what is the order of x at that point. So let's say at v you have some sort of expansion. X is pi v cv pi v to the e plus higher order stuff. So the order of x is e. The order at v of x is e. Okay. And then you plug into here, so you get, let me move over here. Actually, they'll just erase this. Okay, so dx gives you what? So these are these CIs, okay, this is bad notation, CE, sorry. These coefficients lie in the residue field at V. So their differential is just is 0. So if you take dx, what you're getting is the first term you get CE, e pi to the e minus 1 d pi plus higher order stuff. Okay, and d pi is so this locally near v, this generates the sheaf of differentials. Okay, omega 1. And so you get that the order of dx at v is okay, so if p divides e, then the order will be bigger than e minus 1. If p doesn't divide e, it'll be exactly e minus 1. But at any rate, it's at least e minus 1. Okay, and the order of this side, okay, so let's suppose that v is not equal to infinity. If v is not infinity, then dt is a local generator of this sheaf of differentials at v. And so what we get here is just the p times the valuation of x. So we get pe. So this is the left-hand side, the order of the left-hand side, and then the right-hand side, we get the order is PE. And so we get, because they're equal, you get that PE has to equal this, which is at least E minus 1. And so you get that E is at least negative 1 over P minus 1. And if P is not 2, P is bigger than 2, this tells you that E is at least 0. Okay. And so this tells you that if p is not 2, then at every point, at least away from infinity, x has to be a regular function on this curve, p1. Okay, and then you can also do something similar at infinity to at least bound the order of the pole. And so now you get that x is a global section of O of d for some divisor d. And so x lies in a finite dimensional vector space over fq. Fq is a finite field, so a finite dimensional vector space has finite many elements. So there are finitely many possible values of x, and then you get finitely many possible values of y. Okay, so the proof in general is some significantly more complicated version of that kind of argument. Okay, so now an actual question to ask when you see this theorem is, there's this dimension bound that you can ask, well, can you improve the bound? Is it optimal? And so forth. So in fact, it is optimal. So if you take this group, so you take Gn over the extension k to the 1 over p. Now, k to the 1 over p is a degree p extension of k, if k is a global function. So, for example, if you take fq adjoint t, let me erase this. If you take fq adjoint t, then the k is fq adjoint t. K to the 1 over p is nothing other than just adjoining the p through t. Okay. This restriction of GM is a p-dimensional group, and then inside of it, okay, so you have a GM actually sitting inside of this Bay restriction. So at the level of rational points, this corresponds to just the inclusion of k cross in k to the 1 over p cross. Okay, so this is just the algebraic group's analog of this inclusion.
So it's a silly question. So if you take a Bay restriction of an inseparable field extension, is that still a torus, or is it something?
This is not a torus.
Okay.
Yeah, that's actually an important point here. Yeah, this is not a torus. In fact, what we'll see is this quotient is wound. If you take this mod, it's a wound
You're
uniphotic.
about to say that. Never mind. Yes.
Yeah, so
It's on the
but-
slide.
this quotient, then you're taking a p-dimensional group quotient by one-dimensional thing, so you get a p minus one-dimensional group. Okay, so it's out of the bounds of this this theorem. It's well, okay. First of all, first let me say it's unirational. So why is it unirational? Well, it admits just by definition there's a surjection from this Day restriction onto your group, which I'll call U. U is this quotient, right? There's this surjection. And this group is, so GM sits as an open subset of the affine line. It's just the affine line with the origin removed. Okay. So GM sits inside the affine line. And so when you very restrict GM, this sits as an open subset of the Bay restriction of the affine line over K to the 1 over P. And this thing is, I mean, basically, what you do, right, is you just write out one way to sort of see that this is, when you prove the representability of Bay restrictions of varieties, you start with the affine line, and then what you do is you write out a basis. So you choose a basis for K to the 1 over P over K. And when you choose a basis, that basically gives you, so that gives you their P elements, right? You have a basis of size P, and that gives you basically P coordinates on the affine line, and you think of it just living over K. So this Bay restriction is actually, once you choose a basis, this thing becomes affine P space over K. Okay, so this is an open subset of affine space, and therefore it's rational. And so you have a surjection from something rational to U, and therefore U is unirational. And in particular, it has a risky dense set of rational points. So there's lots of rational points. And I claim that it's actually a wound unipotent group. Okay, so let me explain why it's unipotent. So it's smooth and connected because it's a quotient of a smooth connected group. To see that it's unipotent, in fact, it's enough to check that P kills U. And the reason for this is basically, so at the level of rational points, you can do this, and actually you can make this argument work by looking at K algebras, but so roughly speaking, U can be thought of as something like K to the 1 over P cross mod K cross. This is literally K points of U. And if you take something here and you raise it to the Pth power, right? So you take this, you raise it to the Pth power, then you live inside the subgroup. And so this thing is in the quotient, this becomes 0. Okay, so P kills this group, and that implies that it has to be unipotent. And to see it's wound, that's not too bad either. So by definition, U sits inside an exact sequence like this. And now we want to show that there's no non-constant map from the affine line to U. So suppose I have such a map. If it were, so I want to show it's a constant. And in particular, if it's constant, I should be able to lift it to here. Okay. The obstruction, so this now is this can be thought of as a point in U of an A1 valued point of U. And so the obstruction to lifting it to an A1 valued point of this lives in H1 of the affine line with coefficients in GM, which is just the Picard group. And this is trivial. Okay. So there exists a lift. And by the very definition of Bay restriction, a map like this, a K morphism like this, is the same thing as a K to the 1 over P morphism from this thing over K to the 1 over P to this GM. So K to the 1 over P. Okay, so a morphism to GM is a global unit. The only global units on the affine line over a field are just the constants. So this thing has to just be a constant morphism. Constant. So this lift is constant, and that implies that this map down here is constant. Okay, so this is in fact a wound unipotent group. Okay, so we see that the Osterley thing, the bound P minus 1 is really optimal. But the counterexample produced here is, there's a sort of very good reason for the theorem to fail in this counterexample, which is that U is unirational. Okay, so that sort of gives an explanation for why there are lots of rational points. And so the question asked by Osterley, and it's unclear to me, partly, I guess, because my French isn't very good, but to what extent Sarah was involved in this. He lists a bunch of questions asked by Sarah, and it's not clear which ones are Sarah and which ones are Osterley, so I'm not entirely sure. But the question is a very natural one. It's if K is a global function field and U is a unipotent K group with infinitely many rational points, must it contain a non-trivial unirational K subgroup? Okay, so can it only happen in sort of the obvious manner, or for the obvious reason, let's say. So maybe a reformulation of this question might be slightly, at least a priori, slightly stronger reformulation would be, instead of this, okay, U of K is infinite. Instead, if it's infinite, we can look at the Zariski closure of U of K, and we consider the identity component of that, and that's some group H inside of U, so H is smooth and connected. And H has the property that H of K is basically by construction, H of K is dense in H. And so then a natural question instead might be, if H of K is dense in H smooth connected on affine group, smooth connected linear algebraic group, does this imply, so does it follow that H is irrational? And that is an affirmative answer to this question. So I was thinking about, I had some ideas for dealing with it, but sort of inevitably I was led to try to probe the structure of unirational groups in general, and in particular unirational unipotent groups. Let me actually, before I go on, let me say something about the significance of unipotent groups, because you might wonder, why should I care about these things?
Is the fact that you're working over a global function field super important for this question, or is?
Okay. So the question was raised for a global function field, and the techniques I was thinking about, it actually. Well, okay. Let's say the thing that I'm very confident will work, but I haven't actually finished it yet, is replace a global function field with function field of a curve over a perfect field instead of a finite field. Now, of course, more generally, you might ask function field of a variety over a perfect field, and that's the situation. For that is actually more complicated. But yeah. Floating groups, why are they important? Well, they're sort of central objects in the study of general linear algebraic groups. So there are a bunch of different reasons for that. Let me give maybe just one, which in my experience is maybe the most significant. Let's suppose that G is a and suppose, this of course doesn't happen in general, but suppose that T inside G is a split maximal torus. Okay, so this may not happen over K, but it will happen over some finite separable extension. And for many purposes, passing to, okay. So supposing the split maximal torus, you consider the centralizer of T. And now associated to a co-character, so if you have a co-character of T, so that's just a homomorphism from GM to T. If it's sufficiently generic, then you get this open cell decomposition. Okay, so let me explain what all this is. These are subgroups defined of G defined in some way. And the important fact for us is they're both split unipotent. So these are split unipotent K subgroups of G. And this is just the centralizer of T. And this is just, you take the multiplication map. And the important fact here is that this map is an open immersion. So this gives you a dense open subset of G, a dense open subscheme of G, a dense open subvariety. So in particular, if you're asking a question like unirationality, in order to answer it for G, it's the same as answering it for this open subvariety. Okay, and these groups are split unipotent. They're not very complicated. The split unipotent group always, as a variety, is just some affine space. Okay, and so really the subtle object comes down to this centralizer. And now this centralizer, it has the torus contained within it. Maybe I should put one here. This may not be commutative. You have the torus, and then you have the quotient, which I'll call U very suggestively. Okay. Now this U, if it had a non-trivial torus, then the preimage of that torus in here would be a larger torus than the maximal torus. So this U has no non-trivial torus, and it follows that U is unipotent. So it's a smooth connected unipotent K group. And therefore it lives canonically in an exact sequence. Like so, where this thing is split unipotent, and this is wound. And again, because this thing is split, it's very easy to understand mostly. I mean, most questions you want to ask about something like this are easy, or relatively, let's say, easy, at least for certain purposes. And this is the subtle object. So for understanding all sorts of questions about linear algebraic groups in general over imperfect fields, wound unipotent groups are actually the sort of key and most difficult case. Okay. And in particular, for this rational points question, this is true. Right? Okay, so now I'm going to go on a something that feels like a bit of a tangent that will possibly come up at the end of the talk, depending how far I actually get. But I think it's sort of somewhat interesting in its own right, so I'll mention it. So there's this theorem of growth-indeed from, I don't know when, many years ago, not be K-scheme, which sends a K-scheme, but let's say it's over a field, though it doesn't have to be. So K-scheme T to the T morphisms from XT to YT. Okay. So the theorem is that, this is growth indeed, is that this is representable. So the morphism functor is representable by, actually by countable disjoint union of locally finite type K-schemes. Okay, so it's like a countable union of varieties. And so in this context, I asked, for certain reasons, I had certain motivation behind it. I asked, whether you could do something similar where this Y is an algebraic group. And so, okay, the answer can't be yes in general. So for example, if you want to know about whether you have morphism, the moduli space of morphisms from, say, the affine line to itself. So what is a morphism from the affine line to itself? Let's say over, okay, let's even say over K. This is the same thing, it's just a polynomial. Okay. So this is something like tuples of elements of K, where after some point, they're all the entries are 0. Okay, and that's not represented by a scheme, it's represented by an in-scheme. The problem is that you allow the degrees to be as large as you want. So if you bounded the degrees, you said, let's say the degrees are all, polynomials of degree at most n or something, then that would be representable. You would just, you're looking at n tuple or n plus 1 tuples of numbers, and that's just affine n plus 1 space. So this thing is not representable, but okay, so you can't get an affirmative answer when you're for arbitrary algebraic groups in sort of any reasonable situation. But if you assume that your algebraic group is wound unipotent, so if instead I look at morphisms from X into a wound unipotent group, then I can get a good answer, although I have to, there are certain technical restrictions I have to impose. So X is a geometrically reduced K-scheme of finite type. So if you like, just think X is smooth, for example, that's perfectly fine. And U is a wound unipotent K group. And it's sort of this morphism factor, but in all K-schemes, you'll get only the geometrically reduced ones. The reason you have to pose this assumption because this issue with morphisms into the affine line or into GA arises if you have purely inseparable splitting U, you have a problem. So in your category of K-schemes that you allow, for example, you can't allow purely inseparable extensions. So you restrict the geometrically reduced K-schemes. You actually also, this restriction on X that it be geometrically reduced is also essential for reasons I won't get into. But you consider this functor, and the statement is it's representable by a smooth unipotent group with wound identity. Okay. And then, okay, there's some technical improvements you can make to this, which I won't bother with. Okay, well, this is basically just what I just said now. Okay, so as a corollary of this, if you have a smooth group G, okay, so you have now morphisms, you can ask to represent homomorphisms. So if I have a smooth K group G and a wound unipotent K group U, then consider the functor of homomorphisms from G to U on the category of geometrically reduced K schemes. So over such a K scheme T, the functor produces all T group homomorphisms from GT to UT. Okay, and the statement is that this is representable by a geometrically reduced K scheme of finite type. Don't worry too much about all the adjectives; doesn't matter. And okay, if it's commutative, then it's actually just because it harms into a commutative group themselves form a group. So you get it's a group and therefore necessarily smooth and in fact unipotent. Previous result. What you do is you just consider the map from, so you have a morphism from G into U and you want to check whether it's a homomorphism. So what you do, you just consider this quantity and you want it to be the constant map 1, right? And so, okay, you have this map and the homomorphisms are just the pre-image of the point of this corresponding to the constant map to 1. And then, okay, there's some technical thing, you pass to the maximum geometrically reduced K subscheme of that pre-image. Okay. And here's an example. Again, don't worry too much about the details. The point here is, this is an example to show that these things actually vary in moduli. So you're going to have, this is an example over from B into U, this Hom scheme is actually positive dimensional. So if you take these groups, these are all wound unipotent, then you have a non-zero biadditive map from W cross V to U. And so just by definition, that gives you a homomorphism, a non-zero homomorphism from W to this Hom scheme, okay? And so, okay, that already shows it varies in moduli, and in fact, it's not very hard to show that this map's injective, and with more work, you can show it's actually an isomorphism when P is not 2. So when P is not 2, this Hom scheme is just a one-dimensional unipotent group, and when P is 2, it's actually a little bit bigger, it's 2-dimensional. Okay, let me skip all this stuff. Blah. Okay, so now I'm going to go on to something slightly different, but which is related to this issue of unirationality. So, right, recall this result that you learned in, I don't know, first course in Galois theory or algebra or something. Right, you have the primitive element theorem. So if I have a finite separable field extension, then it's generated by a single element. Okay. So of course it's false in general for finite inseparable extensions, and the classic example that everybody, or at least that most people give, is you take any field of characteristic P, you take the rational function field in 2 variables over that field, and then you, okay, so that's your sort of base field, big K there, and then your extension, your purely inseparable extension, which is not principally generated, is you take K and you adjoin the Pth roots of the 2 variables. Okay, and so it's generated by 2 elements, but it's not generated by 1. And then one way to see this is if you take any element of L and you raise it to the P, it lands inside the subfield K. Okay, and so if you take K to an alpha, then the degree over K is 1 or P, depending whether or not alpha is in K, whereas the degree of L over K is P squared. Okay, okay, so now we'll introduce, although I'm slightly actually lying, because we, at least in the case when the extension is purely inseparable, it was introduced by Becker and McLean in a paper, actually it's over 80 years ago, a paper in 1940. But there's a quantity associated to any finite extension, which roughly speaking, it equals the minimum number when the extension is not separable. All right. Okay. So the degree of imprimitivity. Actually, at first I call this. I haven't actually written anything down as yet, so the name is up in the air maybe. But when I first thought of this, I was thinking of calling it the degree of primitivity. And then I realized, well, when it's larger, that's further from being primitive. So it really should be the degree of imprimitivity. But I don't know if anyone has any strong opinions on that, you can let me know. But here's the definition. So if I find an extension of fields of characteristic P, then the degree of imprimitivity of the extension, to note IMP at L over K, it's the integer R such that the degree of L over the compositum of K and the Pth powers in L is P to the R. Okay, so first of all, the L over L to the pk is a purely inseparable extension, and in fact, it's of height 1, because if you take L and raise it to the p, you land inside this subfield. Definition. So it has, its degree is a power of p, so this makes sense to give you an integer. And in the example in the previous slide, so big K is little k to xy, and L is, adjoint x to 1 over p, y to 1 over p. The compositum of K with the p powers in L is just big K. Okay, that's because L to the P is contained in K. And the degree of L over this compositum is P squared, and therefore the degree of imprimitivity is 2, which is indeed the minimum number of generators. Okay. So here are just some properties. Don't worry too much about all of them. Just primitivity is 0 precisely when the extension is separable. It's if you have a tower of extensions where the smaller extension, the tower, is separable, then the degree of imprimitivity of the big thing is the same as the big thing over the middle thing. Okay, and then if you have a finite extension and you pass to some larger field and you pass to this separable extension in this larger field, then the degree, in some sense, it's invariant under separable base change. Okay, and then you have various other properties. It can only go down in tower or go up in towers. Yeah, and then okay, this fifth one is maybe the one that's most related to what I said in the last slide. If the extension is not separable, which is equivalent by this condition 1 or this property 1 to being having positive degree of imprimitivity, then this degree of imprimitivity exactly equals the minimum number of generators required to get L over K. And as I said, when the extension is purely inseparable, this is due to Decker and McLean. Okay. So now one of the useful things about this is you can extend the definition from field extensions to algebras. Okay. So suppose I have finitely many finite extensions of a given field K, the characteristic P, and I have two just bigger fields into which I'm going to stuff all these fields Li. Okay, so E and F. And I have embeddings, K embeddings of the Li into E, and I have some other choice completely unrelated to those embeddings of the Li into this other field F. Okay, then the statement, here's the fact. So the degree of imprimitivity, if you form the compositum of all these fields inside of E, you stuff them in E, and you form the compositum, or you form the compositum inside F, you stuff them here, form the compositum, the degree of imprimitivity, second field extension. Okay, and this is a useful fact because it allows us to define the degree of imprimitivity of any finite reduced K algebra A. Okay, so how do you do this? You have a finite reduced K algebra, you write it as a product of finitely many finite field extensions of K, and then you just stuff them all into some big field. Okay, so you choose a field E containing K, and you just choose K embeddings of the Li's, and then you define the degree of imprimitivity of A to be, you form their composite, the compositum of their images inside this bigger field. Okay, you form the compositum, and you take the degree of imprimitivity. Okay. So this fact ensures that this is well defined. It doesn't depend on our choices of our field or of our embedding. Okay. So now we can define it for algebras. And we, analogously to the properties before, we have some properties for these for this notion for algebras. So for example, the degree of imprimitivity of A over K is 0 if and only if A is an étale K algebra. We have some other properties. For example, it's invariant under separable base change. So if A is some finite reduced K algebra and K prime is a separable extension of K, then the degree of imprimitivity of A over K is the same as that of K prime tensor A over K prime. And
Do you assume that K is commutative?
what?
Do you assume that A is commutative?
Yes, A is commutative. Yes. For me, all rings are commutative. Yes. I don't think about non-commutative things very much. Right. And I should say the fact that K prime is a separable extension ensures that this K prime tensor A is still reduced. Okay, so it's still reduced K prime. All right. Okay, degree of imperfection. So this is just one more notion. So what is this? It's just basically measuring how far you are from being perfect. Okay, so one way to define it is you take the degree of K over its pth power subfield, and you take log base P of that. So for example, if you take K to be FQ, or even just any perfect field, okay, let's say FQ. So if you take K as FQ adjoint T, then the subfield K to the P is FQ adjoint T to the P, because FQ is perfect. Everything in FQ is a P power. And then K to the P to K, you just adjoin T. So this degree is P. And that corresponds to this thing having, so log base P of this is just 1. So the degree of imperfection of this field is a 1. If instead you take FQ adjoin, x1 up to xn, powers will be join powers, and the degree of this over this is p to the n. And so the degree of imperfection is n. More generally, if you have a variety of dimension, well, okay, I'll say this on the next slide. Okay, if there's properties, but okay, K is perfect if and only if the degree of imperfection is 0, because that just says K is K to the P. And then if you have a perfect field and you take a variety, let's say a smooth integral variety, I really don't need to say smooth, I can just say integral variety, but whatever, over this field, then the degree of imperfection of its function field is just the dimension of the variety. So like in this case, you're taking the variety as projective n space, or affine n space, or whatever. Okay. Okay, and the facts that's important for us, if K has degree of imperfection R, so for example, if K is this, you have degree of imperfection 1, then any finite reduced K algebra has degree of imprimitivity at most R. Okay. So for example, if you have a field of degree of imperfection 1, every finite extension is primitive, requires only one generator. Okay. And if you have degree of imprimitivity 2, so let's say you take FQ joined XY, every extension requires at most 2 generators, and so forth. Okay. Okay, so the motivation for introducing the degree of imprimitivity is the following expected results that I expect that I'm working on proving. So the statement is maybe a little bit complicated, but it's not as bad as it looks. So suppose given a wound unipotent K group U, and I've smooth proper geometrically connected curves, x1 bar up to xn bar. So the bars is to denote that they're proper, they're compact. So I have these smooth proper curves over K. And suppose I also have, for each I have a non-empty open subscheme xi of x bar. And I have just choose points xi in little xi and big xi. So I just choose rational points. And finally, let di be the boundary divisor. So it's xi bar minus xi. Okay, and so what I do here now is I let A be basically the sort of algebra corresponding to the total complement of all the xi's and the xi bars. So let me give an example maybe, which makes it easier to digest. So I can take x1 is p1 minus lambda to the 1 over p. I could take x2 to be, let's say lambda is a non-pth power. And I can take x2 to be p1 minus mu to the 1 over p, and x3 to be p1 minus lambda to the 1 over p squared. So where lambda and mu in K are p independent. Okay, p independent means so there are various equivalent ways of stating it, but for example, if you take like FQ join XY, then X and Y are P independent. If you join X to the 1 over P and you join Y to the 1 over P, the degree is P squared rather than P or 1. Okay. So you take the sort of, so in this case, you're taking the total complement here. So what you're doing here is you're taking, the algebra would be you take K joint lambda to the 1 over P, that's sort of the complement in the first curve. And then you take K to the mu, K joint mu to the 1 over P, and then you take K joint lambda to the 1 over P squared. So in this case, this would be your algebra. Okay. You take this algebra and you take its degree of imprimitivity and just call it R. Okay. And here's the result that should hold. I call this rigidity for reasons that maybe I'll explain in the next couple of slides. If n is strictly larger than R, okay, so if the number of curves is larger than the degree of imprimitivity, so for example, in this case, the degree of imprimitivity is what? It's actually just 2. Basically, because if I take so I stuff these all into some bigger field, and I take the corresponding extension of K, I'm getting K joint lambda to the 1 over P squared, lambda to the 1 over P, and mu to the 1 over P over K. That only requires 2 generators. I don't need this one. It's extraneous. So this has degree of imprimitivity 2, which is strictly less than 3, which is the number of curves here of the product. Okay, so this is an example where this holds. So then if I have a K, so I have a map of varieties from this product to U, such that for each I, if I restrict F to the subset where this, on the ith component, I just get this point little xi, it's 1. Okay, so that's my assumption. F has that property. Now then it follows that F should just be the constant map 1. That's the statement. Okay. So the assumption that n is greater than r is actually necessary here. So let me, rather than, you can ignore this slide for a second. Let's look at the situation. So I look at a map from P1 minus lambda to the 1 over P plus P1 minus lambda to the 1 over P to U. So this would be a case where n equals 2. There are two curves. Sorry, this should be mu to the 1 over P. So there are two curves here. And the degree of imprimitivity is also 2. So n is not strictly bigger than r, n equals r in this case. In this situation, actually, you can construct a map with this property. So by stuff I sort of didn't have time to go over earlier, a map with the properties on the previous slide like this is the same thing as a biadditive map from the Weyer restriction GM times, and I can quotient out actually by the copy of GM inside, times the Weyer restriction from K from the other extension and the K of GM mod GM to U. And you can construct such biadditive maps. Okay, so for certain U. So actually, I do this on the next slide. Yes. Okay. So this is so I do this in general, but don't worry about it too much. Basically, in this situation, so if I'm looking for such a biadditive map, I can write down equations. So these are both wound unipotent groups, and I can write down equations for them. So the first group is described by an equation sum I 0 to p minus 1 of lambda to the I, xi to the p is xp minus 1. And the second one is described by the same equation, but lambda replaced by mu. So sum j is 0 to p minus 1 of mu to the j, yj to the p is yp minus 1. And so, so if I take, so the obvious biadditive map here is to take the tuple xi and the tuple yj and map it to xi yj. Okay, so the overall I and j, that map is clearly biadditive. It's additive in each group. And so if I can write down a U such that this will land inside U, then I have a good example. And what the point basically is that sum lambda to the I, xi to the p, times sum U to the j, yj to the p. So this is xp minus 1, and this is yp, sorry, this is yp minus 1. And so what I can do is I can take my U to be the group with, so it's the set of zij's such that, so and I think of zij as being xi times yj. So this will be the group that receives the biadditive map, such that they satisfy basically this equation. So if you multiply this out, you can express it in terms of the zij's. You get it's the sum over all I and j of lambda to the I, mu to the j, times zij to the p. That's xi to the p times yj to the p, and this equals z sub p minus 1 to the rest. So this is an example with n equals r equals 2, where you actually do get such a map as on the previous slide. So the assumption that n is strictly bigger than r is necessary. Okay. So let me discuss some applications of this. I probably won't have time to say too much about the proof or the approach to proving it, but the fact that every finely reduced algebra over a field of degree of imperfection R has degree of imprimitivity at most R allows you to show that if rigidity holds, then you can basically move beyond the curve case. So if I have unirational K schemes, x1 up to xn, and I just choose points in them, and I have a wound unipotent K group U, then if n is strictly larger than R, the only morphism from the product of the xi's to U, such that when you restrict any component to be a particular xi, you get 1, is the constant map. Okay, so this would be a consequence of rigidity. And so this has some consequences to the structure of unirational groups. So if K is degree of imperfection 1, so that includes interesting fields like local or global function fields, then every K-scheme morphism from G to U, where G is unirational, such that f of one, so basically f respects identities, is necessarily a homomorphism. Okay, and this is, by the way, this is sort of where the word rigidity comes from. It's an analog here of the corresponding statement for abelian varieties, right? If I have a map between abelian varieties and it sends 1 to 1, it's automatically a homomorphism. This says the same thing is true in degree of imperfection 1, at least, if the source is unirational and the target is wound unipotent. And the proof is just you apply the previous result to this map, G cross G to H, defined by this formula. So you want to say that this is the constant map to 1. Well, if you restrict G to equal 1, then it's just a constant map to 1. And if you restrict G prime to be 1, it's the constant map to 1. And so the previous result says because 2 is bigger than 1, which is the degree of imperfection, that this map has to be the constant. So F is a homomorphism. And so a corollary of this is that if you feel the degree of imperfection 1, then every unirational wound unipotent K group is commutative. Okay, just by applying this result to the inversion map of U from U to itself. And this is certainly not true of general wound unipotent groups. So this actually, the unirationality is essential for this conclusion. I should say, by the way, though I haven't proven the rigidity result in general, this actually I know how to prove. So this is a theorem rather than something I just expect. Okay, and then you can do something very similar for a higher degree of imperfection. So you have the descending central series, right? So for example, wound unipotent groups are nilpotent, so you know that eventually the descending central series just stops with 1, just ends with a trivial group. But actually, the rigidity result implies that there's a uniform bound on the nilpotency class of unirational wound unipotent groups. So if K is a field of degree of imperfection R, then every unirational wound unipotent group has that its rth derived subgroup, or whatever, descending central subgroup, whatever it's called, is 1. And this is a generalization of the previous fact. As you take R as 1, you get that every such group is commutative. Okay, that's what it's saying in that case. And the idea of the proof is the deduction of this from rigidity is basically just consider the R plus 1 fold commutator map, which, okay, so R plus 1 is bigger than R, and it has the property, if you set any of these entries to be 1, it's the trivial map to 1. So therefore, it has to be the trivial. Okay. All right. Okay, another application, which actually only uses the case when R equals 1. This only uses the degree of imprimitivity 1 case, but is to descending unirationality through separable extension. So it's a fact, and I've seen at least 2 different proofs. One is the Rafa-Laquette, and the other is Colliot-Telen, that for commutative groups, unirationality descends through separable extension. So what does that say? It says, if I have a separable extension L over K, and C is a commutative K group, which becomes unirational over L, and it's already unirational over K. And this is a fact very special to groups. This is completely false in general. It fails even for torsors. So if you take a non-trivial torsor for, let's say, a torus, then it becomes unirational when you extend scalars because it becomes isomorphic to the torus, but it doesn't have a rational point. It's a non-trivial torsor, so it can't be unirational. At least if the field is, well, the field has to be. So one application of rigidity is that you actually can get rid of the commutativity assumption. So if G is a finite type K group scheme and L over K is separable extension, just that G becomes unirational over L, then it actually already was unirational over K. The rough idea of the argument is as follows. So you reduce the case, okay, this is just some technical thing. You reduce the case in which the extension is finite Galois and G equals U is wound unipotent, so I'll say nothing about that. And then you note that unirational groups are generated by maps from open subsets of the projective line. Okay, so this is true almost by definition. Okay, and then you prove the following result. So if I have a non-empty open subscheme of the projective line over a field L, and I have U is a smooth connected unipotent L group, then any morphism from X to U can be written. Okay, so if I have an arbitrary morphism, it might be something like P1 minus 2 points X and Y, say. Right? So what this says is that any morphism from an open subset can be written as a product of maps where each map extends over almost the entirety of P1. So it extends over P1 minus a single closed point. Okay? So you can write this as a product of maps, for example, where one of the maps is from P1 minus X, and maybe, or some of the maps are from there, and some of the other maps are from P1 minus Y. Okay, or more precisely, the restrictions from here to here. Okay. Okay, so I call it a partial fraction decomposition because in the case of the additive group, this is basically just the part of the classical partial fraction decomposition, right? It's saying something like, if I have a rational, right? If I have, let's say, P1 minus, I get rid of the closed points corresponding to, M1 and M2 to, let's say, irreducible polynomials, right? Or let's even say A1, okay? And I go to GA, so that means that I have rational functions whose denominator only involves powers of M1 and M2. Then I can write it as a sum of, so I can write this as a sum of something over just M1 to some power plus something else over M2 to some power. That's basically what this is saying. Okay, so it really is basically the analog of partial fraction decomposition. Okay, and so the idea now is that U is in fact generated by maps from open subschemes of P1 whose complementary divisor is a single closed point. Okay, that's the advantage of this partial fraction decomposition. And a divisor consisting of a single closed point always has degree of imprimitivity at most 1. Just because what you're doing when you look at a single closed point, you're looking at K joint T modulo an irreducible polynomial. Okay, so this field extension of K is manifestly generated by a single element. So the degree of imprimitivity is at most 1 of the complementary divisor. And so rigidity says that if you have just if you have a map from a product of 2 things, then it has to, if it's 1 when you restrict one of the points and 1 when you restrict the other, it is just the constant map 1. Okay, and so you apply this to the commutator map of the map you started with, and you get the subgroup generated by such a map is actually commutative. And so even when you apply this to LSK, you already get an interesting structural result for round unirational groups, which is that a unirational round unipotent group is generated by its commutative unirational K subgroups. This is completely false in general. A general round unipotent group, even a 2-dimensional one, doesn't have to be generated by commutative subgroups. Okay. So now returning to the group of unirationality descends, what you do is you take the map you started with, which generates a commutative subgroup, you take its Galois conjugates, and okay, so this it's a fact, which let me not worry about it, but this doesn't enlarge the degree of imprimitivity in any way of the complementary divisor. And so you apply rigidity to conclude that the group generated by the Galois conjugates is also commutative, but the advantage now is it's also Galois invariant. So it descends to a K group, and this is a K group which is commutative and becomes unirational over this separable extension L. And so now by the commutative case, you get that it actually already was unirational over K. And so you deduce that U is generated by unirational K subgroups and therefore is unirational. Okay. Okay, so I have almost no time left, very little time left. I don't know, how much time do I have? I have till 3. I guess I want to.
Including questions, in principle till 3:30.
Okay, principle till 3:30. Okay, well, I guess we'll see how principled I am. But right, I probably want to then not say too much about the proof of this because it's going to take too long. So maybe I'll stop there and I'll just take questions.
Thank you very much. Are there any questions?
So the fact that you only have it for global fields is related to the fact that your rigidity theorem uses one-dimensional objects, or
No. So I didn't even talk at all about how any of this enters into solving that problem. But the issue is, okay, so I can prove that, suppose U is a, or even actually, it doesn't even have to be wound unipotent, but okay, let's say G is a smooth connected linear algebraic group over, okay, let's say I have a field K, and it's a finitely generated extension of a perfect field. So for example, it could be a finitely generated extension of a finite field, right? And suppose that G is a smooth connected K group, linear algebraic K group, with Zariski dense set of rational points. So I can prove that under that situation, the Picard group of G KS is finite. Okay, so pick of G over the separable closure is finite. Okay, so this I know how to prove this. This isn't a question. I know how to prove that. Now, the problem, okay, so now you're confronted with the following problem. It's a fact that if I have a group that's unirational, then this group is finite. And you could ask, to what extent is the converse true? And over a field of degree of imperfection strictly bigger than 1, it's just totally false. So you can have like forms of GA square, for example, which for which this Picard group is even trivial, but they're not unirational. But then you could say, okay, what if the degree of imperfection is 1? And this is one of the things I'm actually working in. I mean, I have a strategy which I think will work, but I haven't finished it yet. But basically, the difficulty is then to go from here to unirationality. So this only can work in degree of imperfection 1, that jump. But in degree of imperfection greater than 1, you would require something else. Yeah. Sorry, what?
Yeah, they can repeat the question.
Do you want me to repeat the question?
Yeah, if you understood it.
Oh.
Yeah. So the question was, what was the reason that the original Oesterle result is sort of somehow restricted to the case of well, the conjecture you can formulate more generally, but why, at least the arguments I'm thinking of using, why do they only really work when you're dealing with function fields as opposed to, let's say, function fields of curves as opposed to, say, function fields of higher dimensional varieties over finite or perfect fields?
The question in the audience. Yeah, quick one that for your speculation that you can you say something about when all the extant bar are P1?
That's actually the sort of key case. I mean, basically, some geometric class field theory arguments reduce you to that case. That's the key case. That's in some sense the whole point. Yeah.